This lab uses two conservation laws. First, the charge conservation law states that in a single series loop, current can't pile up at a location, so it's the same at every point. Because of this, the two ammeters should read the same value. Second, the law of conservation of energy implies that if you add up all the potential differences around a closed loop, the sum will be zero. To tie voltage and current together, we use Ohm's law that states for an ohmic element, the voltage drop is current times resistance, and because of this, we can measure voltage and current and solve for resistance. We started with the series current containing two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and two ammeters. Before simulating, I predicted the current in series. The resistances add up to 147 ohms, so the current should be 3 volts over 147, which gives about 20.4 milliamps. When I ran it, both ammeters read about 20.2 milliamps, which matched my prediction and confirmed the current is the same throughout. Reversing one ammeter gave negative 20.2 milliamps, which is the same size with an opposite sign, because now current enters the minus terminal. Swapping an ammeter for a voltmeter in series dropped the current to nearly zero, with the voltmeter reading about 2.97 volts, since its huge resistance basically opens the loop. The voltmeter was used to measure potential difference across each segment around the loop, tracking signs. The battery raised a potential about 2.97 volts, the 47 ohm resistor dropped at 0.95 volts, and the 100 ohm resistor dropped at 2.02 volts. Adding these up for a full round trip gives about zero, which is exactly what was predicted. Dividing each drop by the measured current gave 47 and 100 ohms, which was almost exactly what was predicted, and the wire and ammeter came out near zero. Also, putting in a second ammeter in parallel with the 100 ohm resistor shorts it out, with the total resistance dropping to about 48 ohms and the main current jumping to around 62 milliamps. This graph shows the same trip as potential versus position. The battery lifts potential up to about 3 volts, and then each resistor steps it back down with a small step for the 47 ohm resistor and a bigger step for the 100 ohm resistor. The wires stay flat because there is no field along them. Since the electric field is a negative gradient of potential, a steeper drop means a stronger field, which is why the 100 ohm resistor shows the tallest step down. We then move to RC circuits using a 9 volt battery, a 200 millifarad capacitor, and a light bulb. While the capacitor charged, the bulb started bright and faded to dark as the current dropped towards zero. When I disconnected the battery and let it discharge, the bulb flashed bright again and faded the same way. The key result is that resistance controls the timing. The time constant is R times C, so doubling resistance doubles the time. My 10 ohm bulb charged in roughly 10 seconds, and the 20 ohm bulb took about twice as long. To measure the time constant precisely, we used a 30 ohm bulb and recorded the capacitor's voltage as it discharged. Because the voltage decays exponentially, plotting the natural log of the voltage ratio against time should give a straight line with slope negative 1 over RC. The data fell right on a line with a slope of about negative 0.167 per second, giving an RC of about 6 seconds. That matched the nominal value, 30 ohms times 0.2, which was exactly 6 seconds. Thus, the measurement and theory agree well. If a real ammeter was used instead of an ideal one, the real ammeter would have a small but non-zero internal resistance. Since it sits in series, it would add to the total and slightly lower the current below the ideal prediction. If a real battery charged a real capacitor with no resistor, the ideal model says the time constant is zero, so it charges instantly. But in reality, the battery, wires, and capacitor all have some resistance, so charging is never truly instant, and that predicted infinite current becomes a large but finite spike that could overheat the battery, blow a huge, or otherwise damage the capacitor.